Okay, good afternoon, everybody. Matt is not here today, so I'm covering for him. It's a pleasure for me to introduce a colloquium speaker for today, Professor Kevin Parker. Professor Parker is the William F. May Professor of Electrical and Computer Engineering at the University of Rochester. He's also a Professor of Radiology and Biomedical Engineering. And Professor Parker earned his graduate degree from MIT and has served at the University of Rochester as professor, department chair, director of the Rochester Center for Biomedical Ultrasound, and the dean of the School of Engineering and Applied Sciences. His research is in image processing and medical imaging. He is a fellow of the Institute of Electrical and Electronic Engineers, the American Institute of Ultrasound in Medicine, the Acoustic Society of America, and also the American Institute for Medical and Biological Engineering. And he's also a co-founder of a publicly traded company, Virtuoscopic Incorporated. And today he's going to tell us about his work in imaging the elastic properties of tissue. So let's welcome Professor Parker.
Well, thanks for that introduction. It's a great pleasure and a privilege to be here at Arizona Optics. And there's not a tremendous amount of optics here in the talk, but it's medical imaging, and and it's a great story as well, because basically this 20-year perspective that I'm going to talk about, it goes in 20 years. You can see the evolution of a field from just a sort of a scattering of experiments going on here and there across different laboratories to proliferation of many techniques, and then on to research platforms, and then onto clinical trials, and then finally onto commercial hospital-grade equipment that can actually help doctors make diagnoses. So it's a great story, and I wish it had only taken 5 years to get to this point, but it's really taken about 20 years. So we're going to talk about the biomechanical properties of tissue. And first thing, though, I want to step back and say, well, if we went into a time machine back to, early 1990s, and you walked into radiology, you'd see a tremendous evolution of really great imaging systems. I mean, MRI came on board in the 80s clinically, and the older techniques were making new sort of twists and advances year after year. PET-CT's still in the research stage, but it's coming. Molecular imaging is coming, early stage results at different universities. So this is a fabulous array of technology. And in fact, it's so great you would almost say, what's left out? I mean, what more could you ask for than a couple $1 million worth of this kind of equipment in your radiology department? Well, the answer is, it is true, and it's true to this day, that there are still a number of pathologies that can hide in the normal X-ray, the normal CAT scan, the normal MRI, or the typical, I should say. And the reason for that, we're not going to go into all the details of it, but each modality has its peculiar strengths and weaknesses, its peculiar way of establishing contrast or measuring contrast between water, bone, fat, and and especially what we want to see a lot of times, we want to find the tumor in the liver or the prostate or the thyroid or something like that. And the contrast may not be very good. Or there might be diffuse diseases that are very hard to appreciate in a scan. And so actually, there's still a lot of things left out, and one of the more obvious features, obvious now in retrospect, is the biomechanical properties of tissue. And what do we mean by that? Well, biomechanicals, now we're in the realm of mechanical engineering, we're viscoelastic solids, biomaterials. But there are a lot of important things here. The bulk stiffness, whether something feels hard or not, and this goes all the way back to Hippocrates and the ancient Greeks. But there's parameters like the viscosity or the loss parameters of tissue, anisotropy. Muscles are very anisotropic. There's compressibility, other parameters. And I have a slide here from pathology from an excised prostate, because this gets into some of the earliest motivations here, that doctors will palpate lesions on the prostate, on the breast, on the thyroid stuff when they're accessible, and yet many of these will still hide within the normal or typical radiology image, meaning the sensitivity, the specificity is not nearly where we'd want it to be. So biomechanics, it's not just a lesion detection problem either, because there are a number of things like liver cirrhosis, in which the doctors are very concerned about the incidence of cirrhosis and the evolution of cirrhosis in an individual, and they might actually go like this, and they're feeling if the liver is getting harder and harder, okay? And they would really like to have a measurement of liver stiffness that directly correlates to patient condition, the degree of collagen within the, and also is sort of predictive. If it's getting stiffer and stiffer, that's a bad sign, right? And so we'd like to be able to measure that on regular intervals with some kind of scanning technique, hopefully non-invasive. And, again, since Hippocrates and the ancient Greeks and even before, breast cancers had been detected palpably, and lymph nodes, of course, the doctor still will feel your lymph nodes if you say you have the flu, and all kinds of injuries and inflammations. So there's very important diagnostic medicine buried within the experience of whether tissues are hard or soft and where they are. And so what we want to be able to do is go into the middle of someone's liver or thyroid or any organ and basically quantify the biomechanical properties and give that information back to the doctors. So that's where this is all heading. And so again, if we say, but in 1992 or so, no conventional imaging modality at the time could directly assess these properties. And so something new had to come into being. And that something new is this sort of subfield of imaging the elastic properties of tissue. And what I'm going to do is, this is my outline here, and it looks a little formidable, but I'm not going to drag you into details of these. I'm just going to give you a nice look and feel for what this looks like. This is a timeline, though, and the timeline starts back in the 1980s, where there was an increasing amount of technology that could help researchers look at tissue motion and link it to biomechanics and link it to Doppler signals and other measurements of motion within tissue. So out of this comes a number of very nice techniques. And so around 1990, or just a little before, I'll show you what these look like: vibration elastography imaging, then compression imaging, and then MRE, magnetic resonance elastography, and then on to other things as we get up to current time. And again, I got to emphasize that the earliest parts of these start as benchtop experiments, proof of concept, things taped together with duct tape and so forth. And then they move into animal models, in some cases clinical models on patients. They move into specialized research platforms, and then ultimately clinical trials, some of them, and then some of them into the clinic. And meaning your radiologist or your hepatologist can buy one of these things today. And so it's a great progression, and a lot of fun, a lot of enjoyable imaging experiments have been done at different places. Now, U of R here stands for University of Rochester, my home institution, where some branches of this were actually pioneered. In fact, some of my colleagues, it was Dr. Lerner, who was an MD, PhD. He was the one who actually said in sort of plain English to me, he said, "This is really bothering me. I can feel the tumor, but I can't image it. And I'm really bothered by that. There must be something we can do to image the tumor." And he said, "How can my finger be more sensitive and more specific than $5 million worth of scanning equipment in radiology?" And that helped me think about the problem very well. And we developed a branch of this called vibration sonoelastography. And this is what it looks like in the earliest sort of published experiment. Vibration sonoelastography is simply Doppler imaging of vibration within tissues. Okay, and I can kind of skip over a lot of biomechanics and just say, if we have a vibration source on a soft object and we propagate, it'll propagate shear waves into the tissue. And I'm talking about like 100 hertz, 200 hertz. So this would be like low audio vibration. This would be like you standing in front of a bass guitar loudspeaker, amplified loudspeaker. Shear waves will propagate through soft tissue. If there's a hard lesion, then the region that's hard will typically vibrate less. And what kind of vibrations are we talking about? Are we shaking people around? Well, with Doppler, pulse Doppler ultrasound at, let's say, 5 megahertz typical frequency, you could pick up 2 microns sinusoidal steady-state vibration at 100 hertz. So a red blood cell is 8 microns. Okay? We can pick up 2 microns of sinusoidal steady-state vibration. And so we can map out in some kind of brightness scale the flow of vibrations through a tissue. If we see a dark spot, that is indicative of a lesion, a hard lesion. Okay? Hard tissues don't move as much as soft tissues. That's all the biomechanics concentrated into a simple thing. So we published a few papers, and then this is a commercial Doppler scanner, and this is a excised liver of a rabbit liver that has a VX2 tumor in it. And the originals are in color, but basically we can fill in the Doppler. It's very crude. this is a bistable Doppler imaging device, very crude, but still we're able to put together some patterns of high conducting and low conducting of shear waves going through tissues. And a dark lesion is an ominous sign, as we were able to prove in a number of studies and finite element analyses and simulations and tissues. We actually won a Best Paper Prize in 1990, and then we're off to the races. So here's what this looks like. In a lot of our images, we have green as the color scale indicating vibration. So again, and what green turns on at, let's say, 2 microns, and it becomes bright green at 10 microns, something like that. And all we're doing is we're mapping the flow of shear waves through tissues. This turns out to be a very useful thing to do, although, as you'll see, you can go way, way, way beyond that. But in this kind of experiment, we might have a tissue and a lesion. You may or may not be able to see the lesion on normal X-ray or normal ultrasound, normal MRI. We put the ultrasound probe here to image. Somewhere we'll put the external vibration sources. So if it's on my liver, I might put the vibration sources like here. And then this is what a B-scan would look like. And then when we turn on the Doppler imaging and turn on the vibrations, we get images that look like this, especially in phantoms, because we made this thing like 5 times more stiff than the surrounding tissue, so we get these really great images. Anyhow, over time we demonstrated that a dark lesion is an ominous, it's a sign of a hard region in an otherwise soft tissue. Yes, there's a lot of, if any of you do biomechanics, yes, there are boundary conditions, considerations, and so forth, but I'm sort of condensing a lot of results into a generality here, at least, to sort of go through the narrative. So one of the application areas was prostate cancer. And prostate cancer, there are times when it's proven because of a biopsy, and then the person says that, well, they're going to have the whole prostate removed in surgery. So in those cases, we can scan the thing ex vivo, means after surgery. We can scan the whole prostate. We can do regular B-scan. We can do then our vibration imaging. And then later, immediately afterwards, I should say, the whole gland goes to pathology. The pathologist cuts these into 3-millimeter slices or so, examines, stains it, examines it under a microscope. The pathologist then circles the region if there's a region of cancer, and that is the true positive, meaning this, or the gold standard. The pathologist reading on this is considered as good as we can get in terms of diagnosis. So this is the area we're looking for. And this is not a particularly good B scan, but it's representative of some. You can't tell anything on that thing. You can't tell that there's a tumor or not here. The vibration image, the shear wave vibration, and again, this would be 100 hertz, 150 hertz, somewhere in that neighborhood. It's showing a darkening area here, which would be suspicious. So if this were live, you would take this area, and if you were doing biopsies on this person live, which is a standard way of sort of testing, you would at least guide one of the biopsies to this region here and make sure you had that sample. We're sort of, we're not doing that because we have the whole gland after radical prostatectomy. But where this would go clinically is guiding biopsy needles, which is a reasonably important everyday task for a lot of clinics. So in 3D, this is what it looks like. What we did was we did a study on, I don't know, maybe 50 or so prostates, and basically we would have the 3D vibration imaging. So this colored area here means this is an area that looks suspicious. By a radiologist would call this, there's a lesion here. This is the histology result from the 3D slices that were made, and then they're all put together in, the slices are stacked together in 3D. And then we overlap them in 3D using co-registration techniques. So white here means it was positive both on the vibration imaging and on the pathology. So this white area here is a positive overlap. And so we did this. We did this on about 50 patients or so, got reasonably good statistics, although taking the statistics, sensitivity, specificity from the sort of 60% level maybe into the mid 80% level. Still not good enough. We want to get up to like 97, 98% if we can. Professor Barrett's probably laughing at that because not many techniques get up to 97, 98% too readily. We could do this in vivo too as well, and this is an in vivo scan showing a lesion. I don't want to belabor this technique because things move on and there's a lot of other things, but this is some of the earliest starts of really very concentrated set of experiments in a lot of different labs in which people are starting to now go after the specific biomechanical properties. So again, we tried to do the prostate studies in as careful 3D geometry as possible and had a reasonable success in there. One other application of this, and it's kind of a niche application, but turns out to be important. This is a liver that has had a thermal ablation. Now, it turns out that in treating liver tumors, if there's one primary tumor in a liver, there's a treatment in which they'll put in a little, well, actually, there are different ways of doing it, but you could do it by microwave at the end of a needle, or you could do it by HIFU, high-intensity focused ultrasound. They try to ablate the tissue, the lesion, right in the liver while the person is basically mildly sedated. And this, of course, is a pig liver experiment, but the important thing here is that lesions, these thermal lesions, you want to knock out the entire tumor plus a rim surrounding it, and you want to know that you've treated the entire tumor. Well, it turns out on CAT scan, MRI, ultrasound, it's not always easy to understand where the precise boundaries are of the lesion that you've created in a liver. And you have to know that. So it turns out these tend to be very stiff. The thermal ablated lesions are stiff compared to the surrounding normal tissue. So if you do this treatment and you turn on our vibration sonoelastography, you get an image like this in which you have a very clear demarcation of just what part of the liver you've now treated successfully. So it is a niche, but it can be for these kinds of treatments and for the people doing the treatment, it can be a very important addition to the information that they have about where things are. Anyone have any questions at this point about? You can feel free to interrupt at any time.
Yeah.
Yes?
A quick question. How is the sonoelastographic stuff different ultrasound when I go to the doctor?
Well, so ultrasound when you go to the doctor looks like this, meaning it's B-scan, grayscale. And if you turn on the Doppler, you'll get the arterial and the venous blood. And so that's a very good point. So you'll see red and blue, and that'll show you where the blood vessels or the major blood vessels are. So we actually turn that off, and we turn on signal processing. So the green is signal processing that's sort of tuned for sinusoidal steady-state vibration at 100 hertz, the shear wave signal at 100 hertz. I should say the Doppler signal from. So this is a special Doppler signal processing as well, basically. And if you have a strong arterial pulse, that'll still show up with some interference. But basically, we've switched the signal processing over here.
Okay. So in the picture in the upper left there's the dark circle where you've known you've hit it, and then there's a dark region right to the left of it. Does that mean that you missed something else, or is that an artifact of...
That's a good point. That could be an artifact. This is like a dropout artifact here. We're just too far down. That could be some kind of other artifact, or it could be a ligament or there or something. So in fact, on studies like this, we looked for, or I should say, the radiologist then would look for lesions that were consistent in like consecutive stacks, 2D stacks, and were of a certain size. Because there is a certain amount of noise and artifact in the signal processing. Any other questions on that? Yeah.
Could you explain quickly how you get the shear wave velocity, like the data processing?
No, you're talking about calculating the shear wave velocity?
Yeah.
Yes. I will get to it, because actually in these images we're not calculating, we're actually just detecting, and the green is an indication of the amplitude of the shear wave, high or low, basically. And then, but I'll come to the shear wave calculation. Yeah. So that comes a little later. So what happens next is compression elastography, which is just sort of pushing on tissue and then making mathematical reasoning, some of it very simple, about like what's soft and hard. And then we'll get into some of these other things, magnetic resonance elastography, which looks like an MR version of this, but you can do more quantitative things because you've got 3D information. And then we'll get into the shear wave imaging, in which you do calculate the local shear wave velocity. And anyhow, and this moves forward. So let's look at compression. Compression comes out of Dr. Ophir's lab in Texas, a colleague, a friend of mine. And this, all you do is basically, let's say you have the transducer here and you've got your B-scan image. Now you very gently start pressing on the tissue. Press down a little bit. Well, if you're taking images and the computer's running, you'll see the speckle will start to displace, right? And if you're tracking it then with cross-correlation or other techniques, you can calculate a displacement map, all right? Tissue's moving underneath your compression. And then soft tissue will move more than hard tissue. Hard tissue will tend to, really hard lesions will tend to move as a solid body, basically. So actually, the simplest thing you can do is take the directional derivative and get what's sort of a strain map. And the strain will show low strain, dark means hard regions. High strain is displayed as light, and that means very soft tissue. So once again, whether it's the liver, whether it's prostate, well, liver's hard to do this on, but breast tissue, thyroid, prostate, you'll be looking for things like this, where again, you're looking for the dark region, and that means it's a hard lesion, basically. And this comes from GE, and this is one of their earlier versions. Again, it's a liver with a thermal lesion in it. On B-scan, it's hard to say, is this the diameter of the treated lesion? I'm not sure. Here now you get this dark region, extra dark here, but anyway, this gives you additional maybe confidence that you've got a shape here, basically. This is not the best one. This is from like an early stage GE. This technique is so simple to put on your scanner, and it's so simple for the technologist to just do. If they've just got to learn to give a little compression and press the button, basically. That this propagated around the world, and lots of people were doing it within a few years after it was introduced. It's not quantitative, and there are sort of underlying, what would you say, issues with the interpretation of the strain images, but it's kind of a quick, cheap thing that anyone who has a scanner could probably do, and so it's actually propagated. It's being used in clinical trials a number of places. Then MRE comes. MRE comes around somewhere around, this is the cover of Science in 1995. It comes out of Mayo Labs, Mayo Clinic, I should say, in Rochester, Minnesota. And basically, so here's two sources, putting in shear wave vibrations into a phantom, and they're measuring, now what are these stripes? So these stripes are displacement, plus minus shear wave displacements in the medium, only measured using the MR scanner instead of using ultrasound and Doppler. And MR has the advantage you can get a 3D data set very nicely. Ultrasound, Doppler, you're limited to the in-plane and directional information. So you can go quantitative with this in a very nice way. And truly do inverse problems, too, where you invert and solve for the underlying biomechanical parameters. Yes?
Picking up standing waves?
Well, these are, if you have a reflection here, a very strong boundary and a reflection, you will get standing waves, and then you will pick them. But here, I think the shape of this, they're trying to show a kind of a propagating out from these two sources. And there might be some reflection there, but yeah. But it could happen. And so what does this look like clinically then? Well, MR, of course, you got the big bore. The person is going to go into the bore magnet, and it's going to look like a normal MR scan, with one exception. There's going to be some kind of mechanical device that's going to excite the shear waves. Again, 100 hertz, 50 hertz, 70 hertz, 200 hertz, somewhere in there. It turns out that if you get too much, if you get above 150 hertz or so, it's very hard to, the attenuation starts to add up, and you get poor coverage across an organ. So these tend to be at lower frequencies. And I know everyone in here is not an MR expert, but for those of you who are used to it, I'll just say that basically you do your frequency encoding and kind of time it with the motion that you're imposing this motion. You're exciting the shear waves. You control that 100 hertz, and then you kind of synchronize your MR data collection to that, and you'll collect it. You'll do the math, basically, and you'll get a result. Now, this opens, the result is kind of quantitative in 3D, and so you can go into inverse problems then. So what I mean is, now this is from a breast study, breast MR study, because MR of the breast is exquisitely sensitive, but it picks up a lot of false positives. And you want to know, basically, invasive ductal carcinoma, things like that, are they become very hard. And so these are people at Dartmouth. Marvin Doyley's now at Rochester, but when he was at Dartmouth, he was with a group. They were doing the MR imaging plus then the addition of the shear waves. Then they do an inverse solution in which they're solving for the underlying elastic, what's the stiffness and what's the viscosity of the tissue. So in these images, red is very stiff, measured in kilopascals, and blue would be very soft. And so when you see patterns of red like this, that's a bad sign, basically. And they did a fair amount of study. Here's another one where we've got large patterns of red. Red, again, meaning the very high end of the stiffness scale, according to an inverse solution, according to the pattern that had been detected by MR. And so the hope here is that, once again, you could either guide the biopsy. I mean, maybe the most red region is the region in which you should focus the biopsy, assuming you have many maybe suspicious lesions on conventional MR. You use this to maybe zone in on the areas where you want to concentrate your biopsies or treatments. Yes, Professor?
sensitive to spin density T1 and T2. Since the shear wave doesn't involve a density change, it wouldn't affect the spin density. So somehow we must be seeing a T1 or T2 effect here.
Yeah, well, actually, you know, what happens is that, assume, let's say, you're putting in 100 hertz, and so there's this, let's say it's 10 microns of back and forth motion, basically, in the tissue. And then this is the MR sequences, and then over time, basically, you're putting in some kind of gradient that's sort of synchronized to this. So you're sort of trying to pick up the accumulated phase that each little voxel will get by movement. And so you're at the end of the day, you have data it's not T1, it's not T2, and it's not proton density, but it's proportional to the sinusoidal steady state amplitude of the displacement while this was going on. Does that make sense? You're actually coding for motion at a frequency which you know you've put in, basically, because you're putting this shear wave in. I'm not giving a good explanation of it, but basically you're letting the voxels accumulate phase, and later you pull that out, and that tells you your displacement, sinusoidal steady state. And then you throw that into a complicated model to then back out the inverse. What was the stiffness of that tissue? And a whole lot of math goes into that as well. Inverse problem. So in a nutshell, yeah. So there was a lot of hope that these kinds of things could be useful in tracking the progressive growth of tumors, maybe their shrinkage after chemotherapy treatment, and doing things that were otherwise not really evident just, again, from the conventional scans. Now let's go to another technique, which is stands for acoustic radiation force imaging. This came out of Duke, and this is a clever thing. In optics, of course, you know that beams of light will impart a radiation force onto an absorber or a reflector. That's why the little evacuated vein goes around. If you've seen that demo, well, it turns out ultrasound. Say you've got a transducer up here and you're focusing to a little point here within the tissue. There is a radiation force imparted by the absorption of the ultrasound intensity as well. And in fact, it's not negligible. It's like 68 milligrams per acoustic watt or something. So what I'm saying is I could take a beam up here, I can focus down to a point here, crank up the intensity, give a blast of ultrasound, and at that focal point where the intensity is the highest, there's going to be a nice little radiation force push, as if I put my finger into the middle of this right here at 16 millimeter and pushed quickly. Okay? And then once I'm finished pushing, and it might only be 10 milliseconds or something like that, I can go back into conventional mode and I can ping this thing and I can track the displacement of tissues. So this is magic. I can push on a point in tissue, well, not a point, a focal point, and then I can watch the tissue deform and then recover. And I can make up parameters and image that. So that's called an ARFI image, and it's one of the parameters. This might be the displacement, maximum displacement parameter. Now to do this, what I do, I have to push here to make an image of the push displacements. I have to push here, and then here, and then here, and then here, and here, and here. So it takes a little while to do these. It's not a real-time imaging technique till you start applying clever tricks. But this is an image of how much the tissue responded when I pushed on it with a focal point of radiation force. Isn't that cool? So this is really virtual touch, and Philips ultimately, I think Philips Corp ultimately put this on one of their scanners, and they call it virtual touch or something like that. So this is hard. It didn't move much. It's hard. This is soft, right? And again, the classic sign of the hard lesion, right, that we're looking for. So that's a very clever technique, and there are a lot of applications beyond just cancer, but there's, characterization of plaques in arteries. Some of them are more dangerous than others, and so maybe you can by pushing on them virtually like this, maybe you can characterize them, and other things. So it gets better and better. So now everyone in the world is playing around with how they can image the biomechanical properties of tissues, and a lot of clever things are coming. This is a great story for PhD students here because Laurent Sandrin at the University of Paris took a technique where, again, there's a vibration source, and now we're starting to track the shear waves in real time. And by tracking their velocity is directly proportional to the elastic modulus, the stiffness, okay? And so they turned this into a medical diagnostic technique for the liver in particular. And Laurent Sandrin took his PhD thesis and turned it into an instrument and turned that into a company. And now around the world you can buy a device for liver measurements that tracks back to this. And this is what the device looks like. And there's another beautiful thing here. This is not an imaging device, so you can sell it to hepatologists, liver doctors, and they can be trained to put the little transducer right here on the, they train a technician to put it on the liver right about here, or actually between the ribs this way. And the device puts in a little tone burst of shear waves, and then there's an ultrasound pulse echo tracker there too. Not an imaging device, just a tracker. And it tracks the shear wave as it propagates out from the liver, through the liver, I mean. Then it calculates the velocity, and then it reports the number. So your liver is, has a certain stiffness. And it can do this repeatedly. It can look to make sure that the results are consistent and so forth. This device is expensive. Even though it's not an imaging device, it still costs like $100,000. But liver specialists all over the world are using it now. And yeah, so it's a really great success story, I think. But there's more. But there's even more. So the plot continues. Armen Sarvazian, who actually came out of Moscow State, I was telling someone earlier, and he came to the U.S. later in the early 90s and stuff, and he was working on, again, what does this busy diagram do? Well, this is, again, here's an ultrasound transducer, and as I mentioned before, if you turn it on high intensity for, let's say, 10 milliseconds, at the focal region, you're going to make a little radiation force. So it's like a little force acting on this region of tissue. Now, ARFI monitored the displacement and then the recovery of this region. But what also happens, if you give this a quick enough bang, you actually produce a shear wave that propagates out to the right and left. So that shear wave is propagating out from your disturbance. It's kind of like, in a pond, if you go like this at the surface of a pond, the waves will propagate out. If you track these waves by you turn your system over to sort of tracking, interrogation tracking mode. If you track these things, if you calculate the velocity of that wave, then you have a number, and that number is proportional to the stiffness of, and maybe you can go on, maybe you can be more clever and think about viscosity and anisotropic directions and so forth, which people have done. But in its simplest form, this is it. So Sarvazian published a paper, a very influential paper. This would be now 1998. So time is moving on, but theoretically, again, this is time in this direction, and the vertical is displacement, and then this is radial position away from the center of a focus. So again, I've got like an ultrasound transducer. I push the transducer with radiation force, or the tissue. It deforms. It's sort of like deforming, and then it starts to relax, and you see this wave propagating out in one direction. This is like D'Alembert's solution for if you have a guitar string, and you push with a force in the middle of your guitar string, The solution is it displaces, and then these two waves. One travels to the right, one travels to the left. That's D'Alembert's solution. For any of you who've taken mechanical engineering way back when. So you can actually see this in tissue, and then you can measure the spread of this thing. This slope here gives you the velocity of the shear wave, and that gives you the stiffness of the tissue. And there's higher order stuff going on here. Maybe the lossiness of it gives you the viscosity, the loss parameter, and so forth and so on. So if you can build an instrument that can do all this, push, track, measure, display, show the doctor, well, you've got a new instrument that some of the doctors are going to really want to buy. And so he teamed up with another group in France, and they created the supersonic Imagine scanning instrument. I'm going to go back, but I just want to show you what this looks like. So they created a company in France with funding from the French government to do all this, and they built their own platform. And so this is what it looks like. So here's the patient. Here's the normal liver scan. This is what normal ultrasound looks like. You click it into supersonic mode, and I'll explain why it's called supersonic in a minute. And it gives you this color map. Well, this color map is the result of pinging radiation force, watching the shear wave, making the calculations, and then they convert to a number. The number in kilopascals is on this color scale here. So 16 kilopascals, 64 kilopascals. So 64 kilopascals is really stiff for a liver. It means you probably have end-stage cirrhosis and you're going to die. So you would never want to see this. Down here is nice. And so here's the image that's produced, and there's a little special region of interest that you can interrogate, look at the statistics of. But this is a pretty hot commodity in some circles where people are looking at I'm concentrating on the liver. There is actually a lot of applications to the liver, but that's not exclusive. Now, they call it supersonic because of a fact which I have not really explained, and that is the speed of sound of compression, ultrasound compression waves is like 1,500 meters per second. It's fast. The speed of a shear wave in the typical liver medium is like 2 meters per second. It's really slow. So that's a beautiful thing because you've got a fast imaging and pushing technique, and then you've got a slow response. So that's why we can do all this tracking of the shear wave. And in fact, they can put a radiation force ping here, and then refocus, put another radiation force ping just a little below it, below it, below it. And so what I've done is I've put my radiation force almost in a line, and I have all the time in the world then to switch over to tracking mode and then track what now has become this line of shear wave traveling to the right, to the left, with a slight tilt because there's a little time delay. And this is what the image is. This would be the displacement of the shear waves moving, away, basically. You have all the time in the world to track this thing with normal ultrasound and then calculate the number. And then you make this beautiful image here. And hopefully everyone is happy and the measurements are accurate and so forth. Any questions about this?
Can you do that with breast tissue, or has it been on breast tissue as well?
Yes, and in a couple slides, I'll have a couple examples from that.
Cancer has a very distinct feel to it. It's very dense and it's very fibrous.
Yes, and so liver, breast, prostate, and thyroid have been, I think, the 4 major applications for the early rollout of this, of supersonic and its technology. And I do have a slide on that I'll get to. Although the results maybe aren't as, well, we'll see. I'll show you the statistics. One more technique before, maybe one more technique. Yeah, the crawling wave technique. We decided at one point that, to use ultrasound Doppler, there's kind of an established platform. There's hundreds and thousands of Doppler scanning instruments. And we would like to teach them all to be able to measure shear waves in tissue. And so one way of doing this is to put an interference pattern. So we have not one source, but 2 sources. And if you turn one source on in green imaging mode, let's say we turn this one on, you'll get this bloom of green. And then if you turn the second source on, you get the interference pattern. And then if we put a slight frequency difference between the two, you see the interference pattern move slowly across the screen. Now this movie has all the information in it that we need to calculate either a global shear wave speed, which gives us, again, E is Young's modulus. It's the magic stiffness parameter. But maybe there's more. Maybe we can calculate the attenuation of the shear waves, which gives us a loss parameter. And maybe we can do other things as well. But in its simplest form, this is what crawling waves look like. And we can do local estimators of wavelength as well, or local frequency estimators. And we can do localized things. So here again, this is a prostate. This is a B scan of a prostate in a surrounding gel. This is after surgery, put into a gel sort of holding form. We propagate the crawling waves across. So this is one frame of a movie. Things aren't so perfect in tissue. And then we run estimators around. These would be local frequency estimators, and they say that this region has a longer wavelength than that. So again, that's a different speed, and therefore a different Young's modulus. And again, red marks the spot. Here's the histology and the pathologist demarcation of cancer for that example as well. So this is like by late 90s, there's a whole lot of shear waves going on through people, and they're being imaged through Doppler, through MRI, through the special supersonic platform, and so forth, and a lot of good results. We published a paper a little later that talks about, this is a frequency axis here, and all of the all the biomechanical responses to all these different stimuli can be put on a kind of a spectrum of biomechanical response, from very low frequency compression shear wave to repeating compression at very slow. Basically, in biomechanics, you turn the inertial terms on as you go up above 50 hertz into 100 hertz. You go up to 1,000 hertz or more. You're basically varying the importance of the inertial terms in the governing equations that govern the tissue response. And so there's a kind of a unified way of looking at the responses of tissue to all these various techniques that were being developed over time. And that's the reference for it. Okay. To sort of get to the punchline, all of these lab experiments are of academic interest unless they start having an impact on, well, ultimately you get to specialized platforms, research platforms. You start doing clinical trials. And if everything goes well, eventually someone will get clinical trials through FDA approvals. And then you'll have equipment out there in the clinics that can help the diagnosis of people. So let's look at the clinical trials around the world. Now, we're going to talk first about, from the RSNA, Dr. Barr from Ohio, who is a fairly well recognized individual. And I know this is too busy, but this is about breast imaging, and this is with the compression elastography, which is the hand pressing, okay? And Dr. Barr came to this, and he said that after 56 benign and 16 malignant lesions, they got 100% sensitivity and 100% specificity. Now, maybe some people are chuckling in this room because it's really, really nearly impossible to get 100% sensitivity and specificity with these complicated disease expressions. But that was a small study, and he went on, and others went on, and in larger and large studies, I don't think I have it here, but this is compression elastographies. I think he went down to a modest 95% sensitivity specificity for some of his results, which maybe is a little more believable. I don't know. And of course, they usually pick a certain subtype of patients. But again, this is compression elastography, and here's a B-scan image, and then here is the compression image. So on the compression image, dark means hard, and light means soft. And he was noticing that some of these things had this halo effect where there'd be a dark rim and then there'd be a soft interior. And maybe that's realistic and tied to a necrotic core. Maybe not. I'm not sure about that, and I haven't followed that. Dr. Sandrin took his device into clinical trials and on liver fibrosis, and they found a very good correlation of the parameter they're measuring to the liver fibrosis staging that a pathologist would take. And that's great because that enables you then to non-invasively just put a thing on and follow the patient after treatment. Maybe they're getting better after some kind of treatment. You could quantify that. This is what you were asking for. This is supersonic. This is supersonic in the breast. So this is the very elaborate tracking of the shear wave that was produced through the breast tissue. Here's a typical, this color refers to elastic modulus in kilopascals. So, again, red would be the hardest region. Here's what the B-scan looked like originally. And the clinicians involved in this, now we got up to 1,000 patients being done mostly in Europe. The clinicians would then be, after a while, they would get very used to these patterns of hard and soft, and they would be tying in their mind these patterns of hard and soft to what they presumed was the type of tissue or cancer that was present. And what happened after 1,000 patients? What they found, I'm missing the punchline here. Did they get up to 97% sensitivity and specificity? No, not anywhere near that. But they were able to show improvements in sensitivity and specificity and a change in staging of cancers for this group. So there was a positive result, but it's not what Dr. Barr was, what I showed you earlier, nowhere near 97% sensitivity and specificity. So, well, this is the real world. It's a complicated world, and these diseases have very complicated expressions many times. Now, what about optics? This slide comes from, actually it was Steve Boppart's lab in Champaign-Urbana, and I think he was one of the first people to apply OCT to compression elastography, and then others were doing the shear wave elastography. So in compression elastography, again, and actually this is a this could be a I forgot what animal, small animal this is, but they looked at tissues and they looked at some small animal tissues as well, and did compression while measuring OCT. And from the analysis of the signal, you get displacement, you get strain, then you calculate and color code for soft and hard tissues. And so they have developed that technique. And I think there's a number of dermatology applications and ophthalmology applications for this. Although I can't. So where is this all going? Well, first thing is the integration of these. So I've shown you a variety of techniques, right? Like maybe 7 or 8 different of maybe a larger universe of techniques. A handful of them have been integrated onto commercial MRI, meaning if you call up GE, you got MRI, and you say, I want the elastography liver package, you can get the elastography liver package now, okay? Or if you call up Philips and say, I want the virtual touch for thyroid, you can buy that from them if you're, assuming you're a radiologist and you've got the credentials to buy these things, but you can actually purchase them. So that's a very important development for rolling out the testing, the clinical applicability of these. Greater sensitivity to early changes. When a person starts to develop liver cirrhosis or fibrosis, you really don't want to wait till the end stage to know that. You want to know at the earliest possible stage, because that's your greatest chance of turning things around. Similarly, for most kinds of cancer, you want the earliest changes. Developmental models, and including understanding, like in the progression of cardiovascular disease, how does the disease how does it express the biomechanical properties from an early start of the disease? And then how do we pick that up with the imaging systems? Then there's all these additional parameters which I've touched on, but we don't really have time. The sort of higher order parameters of the biomechanics can be determined by clever sort of repositioning of some of these forces and these techniques. And then there are other things, early brain injury, clots, determining whether a clot is a new clot or an old clot makes a big difference in terms of the treatment. Diseases of the muscle, evaluation of the lymph nodes for a variety of things, including sentinel node, looking for the early stage cancer involvement in the lymph nodes, a lot of myocardial tissue applications, and so forth. So it's a very, very dynamic and rapidly moving area. If you want to read more, two of review articles, basically, that we put together. One is this one, the 20-year perspective, which was in PMB just a couple years ago. And then more recently, Marvin Doyley surveys now the inverse problems, because under the hood of a lot of these quantitative techniques is an inverse problem. Now, for the supersonic, the inverse problem is simply tracking and determining the shear wave velocity. For some of them, from the earlier MRE pictures I showed you, the inverse problem is a very complicated thing, including, you've got some model of the wave and you're solving for the unknown parameters. So there's a lot of mathematics involved in that. And so for those of you who love inverse problems and love figuring out how to make them well-conditioned, this is the review paper for you. So that's it, basically. I think, the RSNA and the other radiological conferences, as well as the IEEE, some of those conferences, SPIE, have sections now on this kind of thing, and you'll see these. If you go to those sections, if you go to the conference, you'll see, a bank of presentations with pictures like this, and at least now you know what these colors mean, tentatively. So that's it. How about questions and discussions?